Hello, calculus type people. Hope you're all having a fantastic day. Today we're going to be learning about slope fields and differential equations. Nice little subject here. I love slope fields and differential equations. It's an awesome topic to study. There's actually entire courses in mathematics that are dedicated solely to differential equations. And we'll talk a little bit tomorrow about why, and also the idea of kind of where this stuff came from. But just to start us off here, we have a pretty simple concept or question. What is the derivative of the function? Well, we know that the derivative of the function is the slope of the tangent line, right? So it's the slope of the tangent at a point. Slope of the tangent line at a point on a function. If you are given the derivative of a function, so if you're given the formula for derivative, you should be able to draw a picture of the original, right? So example here says draw the slope field for the differential equation dy over dx equals 2x. So here's what we're going to do, and I'm going to need my ID for this, so I'm going to keep this handy. What I'm going to do is go through and I'm going to figure out what the slope is at each one of these x values, all right? So I've got a point here, 0, 0. If you plug in the 0 for x here, you get 2 times 0 is 0, right? So that means that at the point right here, your slope is 0, and it's just like this. All right? At the point 0, 1 up here, again, you're plugging in a 0 for x, and you get a slope of 0. So it's going to be laying flat horizontally. Let me go in just a little bit here. If you were to plug in 0 again down here at -1, you again get 0. So at 0, 0, the slope of f of x is 0. At 0, 1, the slope is 0. At 0, -1, the slope is 0. So these are all zeros. Now, what you can take from that is anytime you plug a 0 in for x, you're going to have a slope of 0. Actually, I may not use my ID for this. I may just go like that. That means that no matter where this equation is at, kind of goes back to our family of functions. No matter where it's at, it's always going to have a slope of 0 here. All right, and then I can go to my next point. At x equals 1, and I'm going to use y equals 0. I'm just going to pick that. So at the point 0, 1, or excuse me, 1, 0, right here. If I plug a 1 in for my derivative, 2 times 1 is 2. That means that my slope is up 2 over 1. So if you can imagine the line that would go through here, like this. But since this is a slope field, all I'm going to draw is a very small portion of that line at a slope of 2. And you can see that no matter what I plug in for y here, if I go to 1, 1, I'm still plugging in at 1 for x, so my slope is still 2. What that means is that where x is 1, my slope will always be 2. This is what a slope field looks like. And what a slope field does is it puts dots on all your coordinates and it says find your slope here. So what about 2? We'll go to 2, 0, plug in a 2 for x. 2 times 2 is 4. So right here, 2, 0, I have 1, 2, 3, 4 over 1. So if you were to connect these points and then down all the way, this is the slope portion that you end up with. Slightly steeper than the 2, obviously a lot steeper than the 1. So I can actually go and fill this in vertically like this with all the same slopes. Because what this is telling me, and again, this is what a slope field is, what this is telling me is that no matter what the x value is, I don't have anything in here for y, so no matter what the x value is, all of the y's are going to have that same slope. Excuse me, I should have said no matter what the y value is. You pick an x, like 3. Plug it in here. 2 times 3 is 6. And at the point 3 comma 0, right here, you have a slope of 6. And that one's very steep, right? Very steep, very steep, very steep, very steep. Much, much steeper. Much, much steeper. And what this is saying is that no matter where this function is at, when x is 1, your slopes are going to be 2. When x is 2, your slopes are 4. When x is 3, your slopes are 6. When x is negative 1, if you put a negative 1 in here, you get a negative 2. So I'm going to use the point negative 1 comma 0 and graph negative 2. So a slope of negative 2. And then go to negative 2. Plug a negative 2 in there, you get a negative 4. So I'm going to use the point negative 2 comma 0 and plot negative 4, a little bit steeper. And I can go back and fill in all of these with the same slope. Up and down, up and down, up and down. And what I have always thought this looked like, and I'll show you a picture of one tomorrow, what I've always thought that this looked like, if you've ever seen a wind map, if you've ever seen a map of the wind, like I have a, well, you know what? Let me see if you can see it. I don't know if you can see it or not. This is going to be so ghetto. Okay, let me get this out of the way. Oh, but I need to see it. This is so ghetto. Excuse me. Okay, so ghetto. This is a picture of Louisiana. This is a picture of Hurricane Katrina hitting Louisiana. And you see the rotation of these winds? That's measuring the direction of the wind. So you can kind of see this is Hurricane Katrina back from 2005. These little arrows are pointing to the left up here, and then they start circling back around down this way. And then you get to here, and they're coming back around, back around, back around, and they're all rotating around this point. See how all of them are rotating in towards this point? That's what a slope field is. And that's the idea. That's kind of where the idea came from. It's a field full of vectors. That's where the idea for this came from. So I'll show you a little bit more of that tomorrow. But back to the non-ghetto note-taking expedition here. Since there is no y value, the derivative, in the derivative, points with the same x-coordinate have the same slope. And that's what all this is. Since there's no y in here, all your x's will have the same slope. On the previous graph, sketch the solution curve, the original function that goes through the point 0, 1. Now this is an approximation, okay? So the original curve through 0, 1, 0, 1, that's right here. It's an approximation. Now I really want you to see what's going on here, so let me zoom in on this picture. What this is saying is that I have to hit a slope about like this here and about like this up here. Now I don't know exactly what points this goes through. It's an approximation. But you can see that your equation is doing something like this. It looks like a parabola. And I could draw an infinite number of them in here. Where differential equations come into play is figuring out which one this is. Because there's an infinite number of equations that could go in here. Right? So here is my best guess as to what this equation might look like. I know here I should have a tangent line that has a slope of 2. And I know here I should have a tangent line that has a slope of 4. So it's a guess. It's an approximation, and it's a little bit of an art form. But once you get used to doing these, man, they roll off. So let's set this thing up here. It says the equation of the original function. Well, this is a parabola, right? All of this family of curves here, all of these curves are going to be just parabolas. So let's say it's f of x is x squared plus c. And I can also tell that by what would the derivative of this, or excuse me, what would the integral of this be? If this is the derivative, then its integral would be x squared over 2, so your 2's would cancel, plus c. That's where the equation comes from. And if we pick a different point on the graph, what happens to the graph? If we were to pick a different value, like a different value for c, what would happen to your graph? Well, it would shift up and down. So I'm going to write shifts vertically. It shifts vertically. You pick a different point, it's just going to move it up and down. It makes it a new curve. It's going to be this guy's brother or sister from his family of curves. So, in general, when drawing slope fields for a function like dy dx equals 1 over x, since dy dx, your derivative, depends only on x, right? Dx on the bottom with respect to x, all slopes should be the same vertically. That means that if you look at x equals -1, all of these slopes should be the same, and you can see that they are here. If you pick x equals 2, or 3, or 4, or 5, or 6, all of the slopes on that x value should be the same. The same can be said with y. If all you've got is y values, then all of the slopes for those y values should be the same. So horizontally, here's 1. All those slopes are the same. Here's 2. All those slopes are the same. These are two little shortcuts that you can use when you're going through and doing these differential equations. Now let's actually get into a question here. Example 2. It says graph the slope field for the curve that goes through the point 0, 2. Let me back up a little bit. Excuse me. So it says graph the slope field. So I'm going to pick some points here. I always want to start off with my origin, 0, 0. We'll do 0, 1, 0, 2. And I'll do, let's see, you can really just pick a bunch of random points. Since dy dx varies with x and y, I'm going to need a pretty good selection here. So I'm just going to pick some random points. How about 1, 1, 1, -1, 1, 2, 2, 1, -1, 1, and -2, 1. Since I'm dealing with x and y, I'm going to pick a bunch of points right around here. So I've got 0, 0, 0, 1, all that jazz, good stuff all around. I've got zeros, ones, a couple of negatives thrown in the mix here. So let's plug it in. 0 over 0 gives you undefined. 0 over 0 gives you no slope. Undefined slope, right? 0 over 1 gives you 0. 0 over 2 gives you 0. Matter of fact, anytime x is 0, you're going to have a 0. So that makes that easy. I can go ahead and graph those real quick. It doesn't have to be perfect, but it does have to be accurate. How about if x is 1? So 1, 1 right here. Plugging in 1 over 1. Oh, that's going to make it easy. 1 over 1, you're going to get -1. So 1 over 1 is -1. So I'm going to draw a little slope of -1 there. 1, -1. 1, -1. Well, that gives you a +1. So how about 1, -1 gives you a +1. All right. 1, 2. 1, 2 gives you a -1/2. So a little bit more shallow. 2, 1 gives you a -2. So 2, 1 gives you a -2, a little bit more steep. -1, 1. -1 over 1 gives you +1. -1, 1. +1. And this is completely at random, right? It's completely at random. And then -2, 1. -2, 1. So you plug in a -2 up here, you get +2. -2, 1, +2. Now, I'm going to go ahead and fill in the rest of these for you real quick. Really fast here. If you plugged in a 0 for y, no matter what your x is, if you put a 0 in for y, you're going to get a slope of your undefined value, right? It's going to be a vertical line. If you put a 0 in for y, you're going to have no slope. So that's vertical lines. And now this thing's kind of starting to take shape. Let's say we plug in -1, -1. Negative, negative, so 2 negatives over 1 negative, that's going to give you a -1. You can kind of start to see this thing taking shape. And what this is going to end up being here, you can go in and you can fill in all the rest of these later, but what this is going to end up giving you is a circle. And you can kind of see it right here if you can imagine this. And then it says it goes through the point 0, 2, this guy right here. So it's coming down like this, right? You can kind of see it coming down, and then it hits vertical right there, and then it comes back, and then it hits vertical right there, and then it comes up here, and it's going to go through this, and it comes up here like this. And if I could draw halfway decently, this is what you're at. Going through the point 0, 2. You can go in and you can fill in all of those if you want to get a better idea, but it all makes a bunch of concentric circles. Now this one, I'm saying it's a circle with a radius of 2. Circle with a radius of 2. So let's verify that. Formula for a circle is x squared plus y squared equals r squared. So 4. Let's take the derivative and see if we get this. I'm interested. Solve for dy dx and see if we can get that. So I've take the derivative of both sides with respect to x, obviously. You're going to have 2x plus, and the derivative of y squared is 2y dy dx is equal to 0. And solve that for dy dx. So 2y dy dx equals -2x. Divide by 2y. And you're left with -x over y. What we started with. So just a little simplification there. Now, once you understand what a slope field is, we rarely break it apart and have to fill in every single thing, but we will have to at some point. We'll have to break it down and just fill in a bunch of stuff. These are picked completely at random. If you want to go through in a little bit more orderly fashion, you can and fill in more of them. That's fine. It really doesn't matter. But let's go down and let's talk about some stuff that is how these are going to look. First, down here, let me get a good picture on this one. So the question is asking us to match the differential equations with the correct slope field. All right. So here's what I'm thinking. If you can ever come to a part where you have the same x's or the same y values, that's going to tell you what it has respect to. All right. So I'm going to look at these slope fields, and I'm going to look just at this one here, and I'm just going to observe a few things. All right. First, if I look at the x-axis right here, notice that where this y value is the same, right? Where this y value is the same, the slope is all the same. That tells me right off the bat, hey, this thing varies with y. All right, I'm going to go back here for a second. Back to this guy. Since dy dx only depends on y, all the slope fields should be the same horizontally. So, horizontally, are they all the same? If you line this thing up, yep, that's the same. Those are all the same. Those are all the same. Those are all the same. So this one depends on y. So I shouldn't have any x's. So that kind of gets number 2 out of the mix because it has an x down there. All right, and then a couple of other things here. I have a 0 slope up here. And it looks like I've got another 0 slope down here. Now there's a difference between a 0 and an undefined slope. Remember, undefined is vertical. These little tick marks do not mean a vertical slope. Those are just the x-axis being ticked off. Okay, that's just showing. You can see how the function is doing. It's going like this and then coming out like that, right? You can kind of see the ghost of what's happening here. And then these are coming down like this. These are coming in like this. So there's only one of these that really fits that, and that's going to be 3. Let me explain why. What I saw when I looked at this are these two things right here. I see my slope hitting 0 twice. I see my slope hitting 0 twice. Once here, once here. 0 or undefined, doesn't really matter to me. It's 0 twice. Now if I look back at the equations, we already said it can't be 2 because they're all the same horizontally. This one only has 1 y, so that can't give me 2 zeros. This one has 2 y's, so it can give me 2 zeros. So 3 is A. Now let's look at this one. First, are they all the same horizontally? So if you look at the top line horizontally, are all of those slopes the same? No. What about vertically? If you look vertically, are all of those the same? No. So that tells me this thing varies with x and y. Oops, I wrote a W and I meant a y. That tells me it varies on x and y. That's automatically 2. Okay? By process of elimination, you know 1 is C, but let's talk about y. I go to C, the first thing I look at, horizontally, are they all the same? Ooh, they are. Vertically, nope. But horizontally, they're all the same. That means it depends on y. So just a little bit of exercise on matching, all right? And it's a skill. We have to get used to it. We'll do a lot more in class, obviously. But for the sake of time, let's get to this last one here. Find the solution to the differential equation. Okay. It gives me the derivative, and then it gives me my initial condition. My initial condition is the point 3, 5. Oh, excuse me. Yeah, 3, 5. Right? That's my initial condition. So let's figure out what this thing is. Now, to do this, what I need to figure out is how to get rid of this dx. I need all my y's on one side, all my x's on the other. This is a little bit of review. So I'm going to start out with dy equals sine x plus 2 dx. This is called a separation of variables. I've got all my x's on one side. I've got my y's on the other side. Anything that has to do with a y is over here. Anything that has to do with a sine is over here. Now I want the differential equation. That means I want y equals something. Y equals something. Or f of x equals something. Since they gave me y, I'm going to call it y. So I've got dy. I've got the derivative of y. Well, how do I go from a derivative to not a derivative? I need to integrate. So I'm going to integrate this side, and I'm going to integrate this side. Forgive my integral sign there. I'm going to integrate so that the integral of dy is just 1y. The integral of sine x plus 2 dx is going to be negative cosine x plus 2x. And it's an indefinite integral here, so I need my plus c. Gotta have that little c there. And now I use my initial condition to figure out what c is. So what they've done is they've given us a derivative and they're telling us, hey, find the original equation that goes through this point. So I separate my variables, integrate it, and now plug my numbers back in. So I'm going to plug in a 5 for y, negative cosine of 3 plus 2 times 3 plus c. And you can use your calculator here. Most of the differential equations questions, if they're asking for a specific solution, will let you use your calculator. So c is going to be negative 1.990. That's just from plugging in this and then subtracting it from 5, or adding this from 5 and subtracting the 6. And then finally here, my equation is going to be y equals negative cosine x, just bring this over, plus 2x, minus my c, minus 1.990. That is called solving a differential equation. All right, more practice to come.